Hey, welcome back to your favorite calculus class. We're going to do derivatives of logarithmic functions. I'm going to start out with the proof of what the natural log of x is. And so what I'm going to do is I'm going to let y be the natural log of x. I'm going to go ahead and take e to both sides on this. And so we have e to the y equals e to the ln of x. So we got e to the y, and of course e undoes the ln, right? They're inverses. So we got e to the y equals x. And we're going to go ahead and take the derivative with respect to x now. And so we end up with natural log of e, which of course is 1, e to the y, and then chain rule on that, dy dx equals the derivative of x, which is just 1. And so we've got e to the y dy dx equaling 1. I'm going to go ahead and divide both sides by that e to the y. So our dy dx equals 1 over e to the y. Now remember, at the beginning I said y is the natural log of x. So I'm going to go ahead and substitute that in. Y is the natural log of x. So we've got dy dx equaling 1 over e to the ln of x. So dy dx is 1 over x. So the derivative of the natural log of x is 1 over x, right? Where x is positive because the natural log of x, of course, has to be positive, right? There's the graph of the natural log of x, so that's why you've got that requirement there. And it's showing it below with the chain rule. So let's go ahead now and use the fact that the derivative of the natural log is 1 over x, and let's do it for this first example. And so we're going to go ahead and take the derivative. We've got 1 over that. And then we're going to go ahead and multiply. We're going to use that chain rule. So what's the derivative of 9x to the negative 2? Negative 18x to the negative 3. And so it looks like we've got dy dx being 1 over 9 over x squared is x squared over 9. And then we got negative 18 over x cubed. And so our dy dx ends up being negative 2 all over x. All right, we got natural log of the cosecant. So f prime, natural log of the cosecant. So that would be our 1 over the cosecant. And then we take it and we multiply it by the derivative of the cosecant. So I look on my derivative sheet, derivative of the cosecant's negative cosecant cotangent. And then notice the cosecant cancels. So we're just left with negative cotangent. Here I'm going to use the quotient rule on this next one. And it of course involves that natural log there. So the quotient rule says I take the derivative of the top. So the derivative of the top is 0 minus derivative of the natural log is 1 over x. So there's the derivative of the top times the bottom minus the top. And then derivative of the bottom, derivative of x is just 1. All over bottom squared. And so dy dx ends up being negative 1 over x times x is negative x over x. That's just a negative 1. And then I've got minus 1 plus ln of x. And this is all over x squared. So it looks like our dy dx here ends up being negative 2 plus the natural log of x all over x squared. Notice here on this next one, we got a composite. We're going to have to use repeated use of that chain rule. So our y prime here will be the natural log of that. So I'll have 1 over that sign stuff. Okay, there's the derivative of the natural log times. Now I'm taking the derivative of the sine of the natural log. Well, the derivative of the sine is the cosine. So I have cosine times, and now I got to take the derivative of the natural log of theta. So I'll have times 1 over theta. So it looks like we have y prime being cosine of the natural log of theta over the sine of the natural log of theta times 1 over theta. So y prime just ends up being cosine over sine. I have the same input there as cotangent. This is all over theta. So we got cotangent of the natural log of theta all over theta. On this next one here, I would go ahead and use those log properties. So just another quick recap. These are unique to logarithms. So there's your product rule. Here's your quotient rule for logarithms. Again, these are all unique to logarithms, right? So don't forget those. Logarithms, natural log, of course, is log base e, right? So this will work for any logarithm. All right, so let's go ahead and rewrite this, and that'll make this a little bit easier as the natural log of 2x minus the natural log of x plus 3. So if I rewrite it, and when I take this derivative, it's a little more straightforward. Derivative of the natural log is 1 over that, times the derivative of 2x is just 2, minus derivative of the natural log is 1 over that. Derivative of x plus 3 is just a 1 plus 0. So our dy dx ends up being 2 over 2, of course, cancel. So I got 1 over x minus 1 over x plus 3. If you wanted, we could get a common denominator here. So I'm going to give this an x plus 3, x plus 3. I'm going to give this one an x, and an x. So it looks like dy dx ends up being x plus 3 minus x all over x times x plus 3. X is canceled, so our dy dx ends up being 3 over x times x plus 3. Let's go ahead and rewrite this as the natural log of that x minus 1 over x plus 1 all to the 1/3, right? That's a third root. So then we would put that, with that power rule, put that 1/3 in front. And then I'm going to use the quotient rule. So I got 1/3 times, because I'm splitting this using the quotient rule. So it's going to go from 1 logarithm to 2. So make sure you multiply that 1/3 through to both of those, right? You got to be careful when you expand that. So you got 1/3 natural log x minus 1 minus 1/3 natural log x plus 1. Now I'm going to go ahead and take the derivative here. Dy dx would be 1/3. Derivative of the natural log is 1 over that, times the derivative of x minus 1, which is just a 1, minus 1/3. Derivative of the natural log is 1 over that, times derivative of x plus 1, of course, is just 1. So we end up with our dy dx ends up being 1 over 3 x minus 1 plus 1 over 3 x plus 1. Notice they both have a 3 there. And so I'm going to go ahead and give this one an x minus 1. Let's get a common denominator. Give this one an x plus 1. So our dy dx ends up being x plus 1 plus x minus 1. Oops, I just realized that's a minus right there. That's a minus. Sorry about that. That's a minus. And that's all over our common denominator. So I distribute that, and we'll have our dy dx being x plus 1 minus x plus 1. So 1 plus 1 will end up with 2. There's our dy dx. Rewrite this natural log of the all to the 1/2. So we're going to put that 1/2 in front. And then we're going to use the quotient rule. And then I'm going to use the product rule there. So we got 1/2. And I'm going to distribute natural log of the sine of theta plus 1/2 natural log cosine theta minus 1/2 natural log 1 minus 4 ln of theta. Okay. And now we're going to take that derivative. So dy, in this case it's d theta, all right? It's not an x over there. It's 1/2, take the derivative of the natural log, that's 1 over that, and then times the derivative of the sine, which is cosine, plus 1/2 derivative of the natural log is 1 over that cosine, and then derivative of cosine is negative sine, and then minus 1/2 derivative of the natural log is 1 over that, and then times the derivative of 1 minus 4 ln of theta, which is 0 minus 4 plus your derivative of the natural log is 1 over theta. And so dy d theta ends up being, see how I've got cosine over sine, so I got 1/2, I've got cotangent plus 1/2, or oops, minus 1/2 sine over cosine's tangent. And then notice I got negative times that negative, so we got a positive here, plus I got, and then I got 4 over 2, so I got 2 over, and that theta from right there I'll go down, I've got 1 minus 4 ln of theta if I clean all that up there. There's our dy d theta. Our last example here we're going to use with the log properties quotient rule. And now I'm going to go ahead and take the derivative. So derivative of the natural log, 1 over that. Then I'm going to take the derivative of 1 plus e to the x. Well, the derivative of 1 is 0 plus derivative of e to the x is ln of e, which of course is just 1 times e to the x. And then we've got minus, now I'm going to take the derivative of the natural log of 1 over, or the derivative of the natural log of 1 minus e to the x. So it's 1 over 1 minus e to the x times its derivative. So 0 minus ln of e to the x. So it looks like we've got y prime being, remember ln of e is just 1, so I got e to the x over 1 plus e to the x minus times minus a negative e to the x, so that'll end up being a positive e to the x over 1 minus e to the x. Now I'm going to give this, get a common denominator here. I'm going to give this 1 plus e to the x, 1 plus e to the x. I'm going to give this a 1 minus e to the x, 1 minus e to the x. And so our y prime ends up being e to the x. I'm going to distribute this here. I've got e to the x minus e to the x times e to the x, e to the 2x, right? I'm using a to the m times a to the n is a to the n plus n. And then plus over here, I've got e to the x, and then e to the x times e to the x is e to the 2x, or e to the x quantity squared, which again, e to the 2x power, if you want to think about it that way. And notice those two are gone, so we've just got e to the x plus another e to the x is 2 of those e to the x's. All right, let's move into logarithmic differentiation. So this process involves taking the derivative of both sides of the equation. This is why we do it this way, you guys, is to usually release a variable from the exponent position, or it can be used to break up a product or quotient. So it's usually easier than using the chain rule. Okay, can be easier than using the chain rule. Let's show you what we mean here. So I'm going to write this as x times x minus 4. This is all to the 1/3, right? And remember, a times b to the n is a to the n, b to the n, right? So each of those are to the 1/3. X to the 1/3, x minus 4 is to the 1/3 on that. Okay. Now, what we're going to do here, and again, recognize that you could, yes, you could use the product rule at this point, but we're going to practice using an alternate approach, which is called logarithmic differentiation. So we're going to take the natural log of both sides here. And then, now that I have the natural log of y, and then over here what I can do is, since I have a natural log of that, x to the 3rd, x minus 1, x minus 4 to the 1/3, I can break that up with the product rule, since it's now a logarithm. And I can use the power rule, so I can put those 1/3 in front. So now we have, so it's a bunch of rewrites so far. But then at this point, then I say, okay, now I want to take the derivative. So let's take the derivative of both sides with respect to x. Derivative with respect to x, okay? And so what we would have is derivative of the natural log of y is 1 over y. Now, those variables disagree, right? So this is our implicit differentiation. So I got to throw on dy dx because we don't know what y is, right? So 1 over y dy dx. Over here, I'm just taking the derivative of the variables agree here. So the constant stays there, 1/3. Derivative of the natural log is 1 over x. Constant stays there. Derivative of the natural log x over minus 4 is 1 over x minus 4. Derivative of x minus 4 is just times 1. And so we've got dy dx equaling, we want to solve for dy dx. So I want to get rid of this y right here. See how I have a 1 over y? So let me multiply this side by y and this side by y. And so my dy dx ends up being y. Let me write the y in. Well, who is y? Remember, y was the 3rd root of x times x minus 4. So I go ahead and substitute it in. And then times 1 over 3x plus 1 over 3x minus 4. We'll stop right there. All right, here we've got y equaling x minus 2 to the x plus 1. Again, another problem that would be good, useful to use the natural logs so that we can apply our power rule on this so that x plus 1 can come down in front. So we've got ln of y equals, now there's 2 quantities there, so make sure you put that whole thing in parentheses. You got x plus 1 times the natural log of x minus 2. And so now we're going to go ahead and take the derivative at this point. Take the derivative with respect to x, both sides. And let's see what we get here. Derivative of the natural log of y. We've got 1 over y. Chain rule, we don't know what y is, so dy dx, so the derivative of y. Equals, over here I'm going to run the product rule. I've got x plus 1 being multiplied by the natural log of x minus 2. So x plus 1 is my first position, the natural log is in my second. So the derivative of the first, derivative of x plus 1 is 1. Derivative of the first times the second plus the first. Derivative of the second, well, the derivative of the natural log of x minus 2 is 1 over x minus 2. Chain rule, derivative of x minus 2 is just a 1. So we've got dy dx being, and I'm going to go ahead and let me rewrite this first. I got 1 over y dy dx equals the ln x minus 2 plus x plus 1 over x minus 2. Notice we need to solve for dy dx. So I got to get rid of this y, multiply both sides by y. So dy dx equals, now I replace, who is y? Remember, y was that x minus 2 to the x plus 1. That was who our y was. So let's times that. All right, I'm looking at this y equaling theta sine theta over secant to the third theta to the 1/2. So that's secant of theta, secant of theta to the third all to the 1/2. So the 3/2, right? Because we got the square root on that secant to the third. Now remember that secant theta is 1 over cosine. So this is the same as 1 over cosine to the 3/2. So we could multiply by the reciprocal of 1 over cosine of 3/2. That'd take it up to the top. So I'd have theta sine theta times cosine theta to the 3/2. See that? And then if I take the natural log of both sides, I can break that up. So I have natural log of y on the left, but I can break this whole thing up as the natural log of theta plus the natural log of the sine of theta plus the natural log of the cosine of theta to the 3/2. And then I'm going to put that 3/2 in front there. And I'm going to go ahead and do that right now, actually. That 3/2 there. And now let's go ahead and take our derivative here. Derivative with respect to x, derivative with respect to x. And so we have 1 over y dy dx equals, or I'm sorry, this is actually derivative with respect to theta. My apologies. We don't have x's here. Derivative with respect to theta. 1 over y dy d theta here would be 1 over theta plus 1 over sine. Derivative of the sine is cosine plus 3/2. 1 over that cosine. Derivative of the cosine is negative sine. Now I'm going to multiply both sides by y and y. And so our dy d theta ends up being the y. Go ahead and substitute that in. Here's our y up from up top. Our y is theta sine theta over the square root of the secant cubed theta times we have 1 over theta. Cosine over sine is a cotangent. And then notice I have a negative on that sine theta on the next one. So minus 3/2, and I have sine over cosine, which is a tangent. Let's go ahead and find the derivative of a to the x. So let's do its proof here. So if I write a to the x, that would be the same as e to the ln of a, because I know e to the ln of a is just a to the x. So these are equivalent statements, right? So if I go ahead and take the derivative of both sides of that, derivative with respect to x, then what would we have here? So we'd have the derivative a to the x equals, and then I would run, I'd have I'd have ln of a right? Because that's, remember, this is a right there, e to the ln of a. So I'd have ln of a times e to the ln of a to the x. So we'd end up with the derivative of a to the x ends up being ln of a times this ends up gives us a to the x. Derivative of a to the x is ln of a times a to the x. We'll use that quite a bit. So for example, all right, derivative of 3 dx would be ln of 3 dx. All right, how about the derivative of the log base a of x? Well, what I'm going to do with log base a of x is I'm going to rewrite that. If I was to take this derivative, I could rewrite log base a of x using the change of base formulas. That's the same as the natural log of x over the ln of a. And so what you have is, let me rewrite that another way. You have 1 over ln of a, that's just a number, times the ln of x. So the constant stays there. So when you take the derivative, the constant stays there, and then you take the derivative of the natural log, which is just 1 over x. So the derivative of log base a of x is 1 over ln of a times 1 over x. Okay. All right, so we're going to use the rule here. The derivative of a to the x is ln of a times a to the x, right? So we've got y equals 8. Except we don't have 8 to the x. We've got 8 to the x squared. So we're going to have to use our chain rule when we run this. So let's take this derivative. So we've got dy dx ends up being ln of 8. 8 to that x squared, but then chain rule. What's the derivative of x squared? 2x. So our y prime or dy dx just ends up being 2x ln of 8 times 8 to the x squared. Well, we've got the product rule here. That's my first one, that's my second one. I'm going to run my product rule. So dy dx will be derivative of the first times the second plus the first. Now I'm going to take the derivative of that 6 to the negative 2x. So that'll be ln of 6, 6 to the negative 2x. But I got chain rule on that. Derivative of negative 2x is negative 2. And so my dy dx ends up being 6 to the negative 2x. Plus, I'm going to put that 6 to the negative 2x out front of my negative 2 ln of 6. And so if I take out 6 to the negative 2x on both of those, I would leave a 1 minus 2 ln of, 1 minus 2x. Sorry, I had an x in there. Minus 2x ln of 6. I'm going to take use this derivative of log base a of x, which is 1 over ln of a times ln of x. Times 1 over x. So we'll use that rule. Now, first, what I'm going to do on this one is I'm going to go ahead and apply the, I changed my mind. I'm going to apply the quotient rule first. So they're both log base 11, so I've got x to the 14 over x to the 5th. So I can make them into one logarithm. So I've got log base 11, x to the 14 over the x to the 5th. That would be x to the 9. And so that at this point I can say, all right, let's go ahead and run the derivative then. dy dx would be 1 over ln of the 11 times 1 over that x to the 9. But then I got to run chain rule, derivative of that x to the 9, 9x to the 8th. And so our dy dx ends up being, I've got a 9 on the top, and then x to the 8 over x to the 9, that'll just leave me with an x right there. So I've got 9 over x ln of 11. Alright, here I'm going to rewrite this. See how it's same as log base 3. I could write that as 1/2 x squared of x minus 1. And we could even split that up using the product rule. So I got log base 3 of a half plus log base 3 of x plus log base 3 of x minus 1 to the 1/2, but I'm going to put that 1/2 in front. So let me put that 1/2 in front. 1/2 log base 3 of x minus 1. And then I'm going to go ahead and take that derivative now. So dy dx, derivative of log base 3 of a half. Well, that's just a constant, so that's just 0. Plus, again, I'm using the rule, derivative of log base a of x is 1 over ln of a times 1 over x, right? So we got 1 over ln of 3 times 1 over x, plus a half constant stays there, 1 over ln of 3 times 1 over x minus 1, derivative of x minus 1 times 1. So dy dx ends up being 1 over x ln of 3 plus 1 over 2 ln of 3 times x minus 1. We should mention we could get a common denominator on this, you guys. Notice the one on the left had an x, this one needs an x and an x. The one on the right has they both have an ln of 3, but the one on the right bottom has a 2, so I'm going to give this a 2 and a 2. The one on the right has an x minus 1, so I'm going to give this an x minus 1 and x minus 1. And so it looks like our dy dx would be 2 times x minus 1, so 2x minus 2 plus x all over 2x, x minus 1, and an ln of 3. So another way to write this would be 2x plus x, 3x minus 2 over 2x, x minus 1, natural log of 3. Let's go ahead and put that ln of 10 in front here. So we got y equals the ln of 10 times, and then I have log of the top minus log of the bottom. So log of the sine and the secant minus log of e to the x times 3 to the x. So we got ln of 10. Now I'm going to split that up. So log of the sine plus log of the secant minus, I'm going to split this up, log of e to the x plus log of 3 to the x. So that minus will go through to both of those. Okay. So we got y equals ln of 10 log sine Alright, so we're right there. And then we're going to go ahead and let's take this derivative, dy dx. So we have our constant stay there, ln 10, and now we're running our derivatives here. So I got 1 over ln of 10, remember it's log base 10, times 1 over sine of x, times the derivative of the sine is the cosine, plus, now I'm running the derivative of the log here. 1 over ln of 10 times 1 over secant. And then I've got the derivative of the secant, which is secant tangent, minus 1 over ln of 10, 1 over that e to the x. Derivative of e to the x is ln of e to the x. Of course, the ln of e is just 1. Minus 1 over ln of 10, 1 over 3 to the x, times the derivative of 3 to the x, which is ln of 3 to the x. Now notice when I distribute my natural log of 10 in the very front, it's going to cancel. See how it's going to cancel all those right there? So I'm done with that. So my dy dx ends up being cosine over sine. I got cotangent. Plus, notice these secants cancel right there. So I'm just left with the tangent right there. And then I've got, see how I've got e to the x over e to the x, so minus 1. And notice my 3 to the x's right here cancel. So I've just got a minus the ln of 3. So this cleans up pretty nicely after all. So, well, thanks so much for watching derivatives of logarithmic function and taking notes. We'll see you next time.